In today's class, we are going to start with the S parameters. Quick review of S parameters before we move on to the next block. Okay. Before we do that, as I promised yesterday, I'll draw the picture of the symmetric inductor. So let me draw it in thing here. Let me see. I think I've got it correct. So let me see. Yeah. And this is your center tap if you want. It'll look like this, right? Because you have two crossovers. The mistake I was making yesterday was that you need 3 turns, because the minute you have two crossovers, you need an additional turn, right? As I said, once you just think about it for a few minutes, it's quite obvious, right? Okay. I think we are pretty much done with inductors and transformers yesterday. So you folks want to copy this or something like that? Okay. I'll leave it up for a couple of minutes. So today we'll quickly review in 10-15 minutes. We'll review S parameters before moving on to the next topic. So note that if you want the center tap, you need a third metal layer to underpass both the overpass and the underpass. If you don't want the center tap, then you can just do it with 2 metal layers. You need to do the crossover such that each half of the inductor sees one crossover on the lower metal each, so that it will be symmetric on either side. Okay. By the way, if you are going to use it on in a fully differential circuit with a center tap, right? Note that the two halves of the inductors have a strong mutual coupling factor already. There is no special advantage to using a transformer in this case if you're going to use it as a differential circuit. Okay? You can also build a transformer, but it may not be needed here if you're going to use the center tap. If you need access to all 4 ports, then you will have to build a true transformer. I hope you understand what I'm saying. So for example, if you had two halves of the circuit like this, so you had some circuit here, some circuit here, you had the two differential halves like this, right? So maybe the center taps are like this. Then you need a true transformer. Okay, just wanted to point that out. Okay. So we looked at 2 separate transformers. The more commonly used one in fully differential circuits is the planar transformer. right? It will have lower coupling factor because you are assuming coupling across the, onto adjacent lines which are already very wide. Okay. Whereas if you have a vertical transformer, you'll get a very strong coupling factor, but the transformer itself will be asymmetric. Okay. You can move this here. So, quick review of S parameters. So remember that if you have a two-port network, you have various types of parameters. I think what are the parameters that you folks have learned? Z parameters, Y parameters. I think you know of G parameters and H parameters. Any other parameters you have studied? A, B, C, D. Okay. A, B, C, D. All of you have studied A, B, C, D parameters? You have not. How many of you have not studied A, B, C, D parameters? Okay. The others, where did you study A, B, C, D parameters? In the circuits course. How come people, I think you guys are in the same batch, right? How come you didn't study but these guys studied? Okay. So, well, quick summary. I'm not going to cover ABCD parameters explicitly here, but note that you have various pairs of quantities associated with this two port. You have voltages and currents at the input and output, right? If you decide to monitor the voltages and currents, okay, so the normal way is to look at V1, V2 as the input and output voltages, I1 and I2 as the input port and output port currents. These various parameters relate these quantities, okay, to the others, to some of the others, okay. Z parameters happen to relate V1 and V2 to I1 and I2. Okay. Y parameters happen to relate I1 and I2 to Z1 and V1 and V2 and so on, right? G and H are hybrid parameters. Okay. ABCD parameters happen to relate the output quantities to the input quantities. They relate I2 and V2 to I1 and V1. Okay. You also have inverse ABCD parameters which can relate the input port parameters to the output port parameters. I hope that makes sense now, right? You can now choose any pair of parameters as the independent parameters, the other two as the dependent parameters, right? You'll get a matrix relationship. Okay. Now, specifically in the case of distributed systems, okay, you don't necessarily talk only of voltages and currents. All of you know from transmission line theory that how many of you have not taken transmission lines? Okay, good. All of you have. So you have rudimentary knowledge of transmission lines. That is good enough for this course. The point is, you know that the minute you have distributed systems, okay, you folks know that if impedances, maybe you don't know this, if the impedances are not matched, okay, I'll put it in a different way. At any node in the distributed system, you have what is the instantaneous voltage and current waves can be thought of conceptually as the sum of a wave traveling in the forward direction from, let us say, input is on the left and output is on the right. So you can think of, in any distributed system, you can think of a forward traveling wave and a reverse traveling wave. Okay? And the reverse traveling wave, maybe the incident wave is actually coming only from one direction. So let us say input to output. Let us say it starts only from one direction. The input is applied from one direction. But what happens is that if there is a mismatch in the impedances looking in the forward direction and the reverse direction, okay, what will happen is that part of the wave, incident wave, gets reflected back in the reverse direction. Obviously, there is a phase shift between the forward and reverse waves. Especially if the input is coming from one direction, it has to travel to the point where there is an impedance mismatch, and then part of it gets reflected back and part of it keeps going forward. Now you can see that these two waves have different phases, right? At every point where there is a mismatch, okay, there will be a reflection. Okay, so since this is always true in distributed systems, it is useful to characterize two-port distributed systems in terms by relating the incident waves and the reflected waves. Okay, does this make sense? So because you have both incident and reflected waves, note that if you relate these, they will always be somehow related to the impedances. So these two-port parameters that relate incident and reflected waves can in turn eventually be related to the Z parameters or the Y parameters, etc. because it is related to the impedances. Okay? I think that should suffice as a quick oral introduction to the concept of S parameters. So for any two-port, or in fact any N-port, this can be done for any N-port system. I will take the example of a two-port. So you have what are called S parameters. Okay. S parameter. So if I were to denote the incident parameters as, let us say, Vi. So Vi1 and Vi2, and the reflected parameters as Vr1 and Vr2. Okay, note that somehow S parameters will relate Vr1 and Vr2 in terms of Vi1 and Vi2. Okay, and it is customary to renormalize these parameters by relating not just Vi1 and Vi2, but using a normalization factor of some, so I'll call that 1 over root Z0. Okay, these incident and reflected waves are going to be normalized using some factor 1 over root Z0. In other words, I'm going to represent Vr1 by root Z0 and Vr2 by root Z0 in terms of Vi1 by root Z0 and Vi2 by root Z0. Oops, just 1 minute. Very often, um, if you pick up a textbook, you will find that very often these renormalized voltages and currents are expressed as variables A and B. Okay, that's what you'll find. So the reflected, the incident parameters are A1 and A2. So A1 is VI1 by root Z0. A2 is VI2 by Z0. And the reflected parameters are B1 and B2. Okay. Now, why do we apply this normalization factor? Any ideas why we would want to do it? If you square it, you get the power. I think you must have, those who studied S parameters, this is something that is mentioned always, right? So A1 squared is incident power at port 1, A2 squared is incident power at port 2, etc. So A1, A2 are normalized voltages, but A1 squared, A2 squared, B1 squared, B2 squared are power quantities. Okay. And in general, in microwave theory, you will find that you talk mostly in terms of power because the standardized impedances are all 50 ohms. Okay. So you always deal in terms of power, right? So much power as incident, so much got reflected back, so much got pushed into the system. When you deal with two-port systems, you talk about power gain, right, of the two-port and so on, because you're talking about matched impedances at input and output. Okay. Now, this is a quick introduction to S parameters. Okay. If you wanted to see, if you had a perfectly matched system, right, Zin would be equal to Z0. Zout would be equal to Z0. The two-port will be loaded with Z0. It will be driven with Z0. Right? A perfectly matched system, all impedances will be Z0. Right? In our case, Z0 is 50 ohms. Okay? So normally, if you want to characterize any, let's say you have an unknown two-port. I want to measure its S parameters. How will you do it? So now I'm going to assume it's a 3-terminal two-port. Okay? That's easy. So what I'm going to do is I'm going to drive it maybe Z0. I'll just call this Z0 directly. The two-port itself may not be matched, right? But if I want to measure the S parameters, I would drive it with a 50 ohm matched source. I cannot drive it with an ideal source. Okay? I will drive it with a 50 ohm matched source. Because if I drive it with an ideal source, right, since impedance is not, actually you don't know what the input impedance of your circuit is. But you want to make sure there is an incident power, not an incident voltage. Right? So that's why you characterize it when everything is driven with 50 ohm systems. Suppose you are checking a one-port system. Okay? You can actually, S parameters can be defined for any number of ports. If you're talking about a one-port system, it will simply look like this. Okay? So literally, you will only have one pair of quantities, Vi1 by root Z0 and VR1 by root Z0. So A1, B1, B1 by A1 is of course S11. There is only one pair. This is also called the reflection coefficient. Okay. Note that S parameters in general have magnitude and phase components. They are complex quantities because the power that comes back can have a phase shift. The voltages and currents that come back can have a phase shift, not the power. The voltages and currents that get reflected back may get reflected back with a phase shift. Okay. So, and same is true for gamma also. So I'll just make a note here. Okay. Now, of course, if you have a well-matched system, right? If you have a matched impedance, okay, Zin for your one port is equal to Z0. What will happen is that there is no reflection. Okay. Gamma is 0. Okay. In general, gamma, the magnitude of gamma, in fact, normally since you deal only with matched systems and you're trying to match systems, match impedances, you don't worry too much about the phase for the reflection coefficient. Okay. There are some specific circuits where you worry about the phase of reflection. For example, if you're building a phase shifter, you have to worry about the phase. But most systems, you are interested in the magnitude, making sure it's extremely small. Okay. You can show that the reflection coefficient is equal to the Zn minus Z0 by Zn plus Z0. Okay. And you want to make this as small as possible. If you have a, why did I bring in the one port suddenly? Because if you have a two port, okay, let us go back to the two port. For a one port system, the reflection coefficient definition is clear. But if I move to a two port system, note that so let me, if I were to explicitly write down the equations relating B1 and B2 in terms of A1 and A2. What is B1? S11 A1 plus S12 A2. B2 is S21 A1 plus excuse me. What this is telling you is that the component coming out, note that if you were to measure the power that is received from the two port at the input port, that is, you are measuring B1, that has two components. One component is what you are applying at port 1, which is reflected back, that is this portion. But there will always be a second component which is related to the transmission, reverse transmission through the two port. Okay. If you just measured B1, okay, it will have both components. So what I'm trying to point out, if you try to measure the reflection coefficient through a two port measurement, if your two port is not unilateral, right, what you will measure is a combination of both powers. It is not just S11. That's the point. Gamma is not just S11 for a two port. Okay, if you had a unilateral block, if S12 was 0, S11 is of course B1 by A1, which is the traditional definition of gamma. Make sense? Okay, so just be careful. The reason I'm explicitly pointing this out is because some people in common parlance nowadays call S11 as the reflection coefficient, but it is true only in a specific condition. In most cases, if you're dealing with amplifiers, this would most probably be true. You want unilateral systems anyways, if you deal with active blocks. If you deal with passive blocks, it is clearly not true. Okay, that is just something to keep in mind. Okay, now S11 and S22 give you the give you an idea of whether the input and output of the two port are well matched to 50 ohms to Z0. Okay, so S11, S22 decide whether input and output ports are matched. To Z0. What about S21? S21 tells you if you apply some power A1, it tells you how much power is delivered to the load through B2. B2 is what flows into the load. I have not explicitly shown the load here, but the load would be connected at the output port. So S21 gives you an idea of the power gain. Okay, because B2 squared by A1 squared is the power gain of the system. S12 is the reverse transmission. Okay, why does that matter? We have been trying with LNAs to unilateralize the circuit. Okay, for various reasons. Number one, input and output matching network should not interact with each other in the reverse direction. But more importantly, S12 will give you an idea of stability. Okay. Okay, and based on the value of the S parameters for an active two port, you can come up with conditions for stability. Okay, any questions? It's okay, it's pretty straightforward. Any other loose ends that we need to do before we move on to go back to LNAs to wrap that up? What does that mean? Actually, I have related only to B1 and A1, which are renormalized voltages. Okay. Of course, it is. What does that mean? No, B1 squared and A1 squared are the powers. Okay, B1 and A1 are the voltages. Okay. Yeah. Okay. But obviously, if you relate B1 squared, A1 squared, right, then you can relate the S parameters to power quantities also. Naturally, you can. Okay. Okay, then if not, in the remaining time, let us just go back to one final type of LNA before we move on to the next topic of mixers. Yes. S12, correct. Brief idea of what? How to find stability. I'll give you the stability factor when we come to power amplifiers. Okay, we will do that when we come to the power amplifiers. The reason is you have explicitly made the LNAs unilateral, right? By adding cascodes, etc. And that normally works quite well. In the case of power amplifiers, the devices are so large that S12 will be very small. If you measure S12 for LNAs at these frequencies, you should normally not have a big problem with stability. You'll have a problem with stability if you're designing 28 gigahertz LNAs, but not with 2.4 gigahertz LNAs. Okay? But I'll just point out that for the idealized LNA, even without the cascode, okay, there is no reverse transmission. S12 should be 0 for the ideal LNA. Okay? So CGD is what decides S12. Okay? It's an CGD is of course inherent to the device, and therefore it depending on the size of the device, you will basically get some value of CGD, and depending on the frequency of operation, you will get some S12, right? You, of course, we fix that by adding the cascode, right? We fix that by adding the cascode. That works well at very low frequencies, at a couple of gigahertz, 3, 4, 5 gigahertz. If you go to 28 gigahertz, this doesn't work well. So you have to do other explicit ways of making the circuit unilateral. Okay. Now maybe towards the end of the course, we can have a separate set of lectures if we have time on what to do in how will your design depend if you're building millimeter wave circuits instead of regular RF circuits. Okay. But for now, let us leave it at this because we're going to come back to this during power amplifiers. Okay. So just hold your thoughts. I mean, hold your questions till then. Because in power amplifiers, these devices will be extremely large. Even at 2.4 gigahertz, CGD will be extremely large. All your capacitance will be extremely large. So S12 will be very small for power amplifiers. Okay. I think I'll just note one last thing. In traditional, in analog circuits and analog ICs, how do you analyze stability? Of what? And how do you find the gain margin, phase margin of the loop? You break the loop because you are trying to apply explicit feedback. So you have control over breaking the loop. How will you break the loop here? CGD is inside the transistor, unfortunately. You cannot break the loop even if you want to because it's inside the transistor model. Whether it is discrete circuit design or integrated circuit design, you cannot break the feedback loop. You understand? So that is why you will have to come up with other ways to measure stability of the system. Okay? It is clearly related to S12. Clearly S12 tells you how much of the signal is being fed back and with what phase. So you can relate it. Okay? But I just want to point out that you cannot explicitly break it. Okay? How? Yes, but you can theoretically break it. Let us say you can theoretically break it. Now you want to simulate it and confirm that your theory is correct. How will you do it? Then it's useless. So your theoretical analysis is useful as a design, part of a design procedure, if you can back it up with simulation and finally test it out on the main circuit. Otherwise, it's not good. Okay? Okay? So just one other variant of the common gate amplifier before we close out the topic of LNAs, and from next class we'll move on to mixers. Okay? So let us go back to your common gate LNA. Okay. Let's take this rudimentary common gate LNA. Now, if you remember, the common gate LNA gave you active input match to 50 ohms, 1 over GM. It gave you broadband operation. The problem was that its noise figure was quite bad, right? That was the problem. So one variant of the common gate LNA, so this is your common gate LNA. One variant of the common gate LNA was the noise cancelling LNA. What we did was we sampled the noise, not sampled the noise. We basically found out a node inside the circuit where the noise of the common gate exists in a scaled fashion. We took it to the output and subtracted it from the output. Okay. It turns out that there exists one more way to improve the noise of the common gate structure. To do that, let us go back to basic circuits, to your basic common gate amplifier, not just your LNA. So we'll take a step back and if I look at just from signal point of view, well, I can since I'm anyway applying voltages, right? The input current is basically VO by GM. Sorry, GM times VS, right? So I in GM times Vs, and that flows through RD. Okay, V out is basically GM RD times Vs. If I were to apply an ideal voltage source. Okay, now if I were to take this, this is called a regular common gate amplifier. You can use this as a cascode for your regular common source also. Now, for this common gate structure, there exists a variant of this called gain boosted structure. Okay. If instead of grounding the gate of the common gate amplifier, okay, I were to apply a signal that is proportional to my input signal, right? I want to see what will happen. But now let's take a step back. Okay. Note that the loop gain has to be negative so that you're applying negative feedback. Okay. So note that this gain has to be negative because from the gate to the source of the transistor, you have a positive gain. So this gain, first of all, has to be negative. So I'll write it as minus A. Okay. So first I want to find out the input impedance of the structure. Assume RDS is infinity. Find out the input impedance of the structure first. Okay. Please find it out. Is okay? Sorry. Okay, so Vs by Is is 1 over Gm into A plus 1. Okay, so because of negative feedback, the common gate amplifier looks like an even better current controlled current source. Remember that the current controlled current source needed to have very low input impedance. You already have very low input impedance 1 over Gm. If you apply negative feedback, it looks even better. Okay, it looks even better because there is a factor A plus 1 by which it gets magnified, the low input impedance. It gets reduced. Okay. Now you can go back and do the same thing to the RF LNA. Okay. So you go back to your and try the same gain boosting structure. Okay. The things you have to remember are that you are now trying to explicitly input match the LNA, not just try to achieve very low input impedance. Okay. So Rin is basically 1 over A plus 1 times Gm. Okay. So for example, if A was 1, if you just had an amplifier of gain minus 1 going from the input to the gate of the transistor, okay, the input impedance will just become half of what it used to be, right? If you had a gain of minus 1, okay, gain is 1 over, input impedance is 1 over 2 Gm. So for example, if you needed in your original common gate amplifier, you needed Gm to be 20 millisiemens, 50 ohms for 50 ohms. Now you only need 10 millisiemens, right? So potentially you could use smaller transistors, lower current, if you could do this. Okay. Now the point is, if you don't want to affect the noise, you need to look at two things. You will need to see the effect of this feedback in the common gate LNA on the noise figure. That's number one. You want to see whether this negative feedback is improving noise or degrading noise. Okay. So you need to see what happens to noise figure. Okay. Because now you have actually made the GM of the common gate transistor smaller. So you need to go back and see what that effect also has. Okay. Then what about noise of A? Amplifier A itself will add noise. So you need to check for that. Right? And finally, you need to now figure out what A will look like. Right? You can assume A has some noise, figure what will happen. Then next step is to figure out what does A look like? What kind of amplifier can you choose there? Okay. So maybe in tomorrow's class, we'll look at, in the next class, next week's class, we will look at all of these. Okay. And we'll come up with a new common gate, modified common gate LNA structure. Okay.